afternoon, folks. Mr. Myers here for Honors Chemistry 1, 6th hour. Some of you are really excited to be here today. If you guys can bear with me, my voice is still crap. So I want to start off here showing you a screenshot. I found this. It's pretty funny. Help, help, I'm dissolving. But bears are insoluble. That's easy for you to say. You're not polar. Isaac, that one's just for you, buddy. All right, so what we're going to be covering this afternoon is intermolecular attractions, as well as then their effect that they have on things like boiling point and surface tension. The boiling point aspect is something that will play a role probably into January when we get to physical properties and change. Offs to a minimum. Anyway, so like boiling point will come about in probably our last unit of the semester, but you've all heard of boiling point, and so we're going to address it a little bit, and then we'll review it again in January. And then the other thing I want to bring up too is surface tension as it relates to the lab that we're doing tomorrow. So make sure you're here for that tomorrow. It's a fun one. I mean, really, we're going to be putting drops of liquid on a penny, doing 3 trials for each liquid and finding out which one holds the most. The one that holds the most is the greatest surface tension, but we can apply that in the context of intermolecular attractions. Okay. So we'll do it again. Okay. All right. So intermolecular attractions. Here we go. All right, so intermolecular attractions, the way we define it, they're attractions, first off, between 2 or more molecules. Okay, so they're attractions between 2 or more molecules, and we actually get this from the name. If we break the name down for any of you that have taken Latin or even etymology type courses or have the experience with that, we have intermolecular attractions. We have attractions. Inter means between, and then molecules. So these are attractions between molecules, just as the name states. If it was intramolecular, instead of inter but intra, they would be attractions within the molecule. So one example I think of is if you ever go and work for a company and they have their business intranet, it's like their network that they have within just the company or corporation. It's not tied to the outside world like the internet is. So the internet is between other things, not just within your company, and an intranet is within. The intermolecular, between molecules. So these are attractions between 2 or more molecules. And something to keep in mind with this is that these attractions do not, I should capitalize this, do not, okay, it's a big capital not, they do not involve the exchange of electrons. So the importance of this statement, if it has the exchange of electrons, that's what we would call bonding. Right? Chemical bonding involves the exchange of valence electrons. If the electrons are transferred from metal to non-metal, we call it what? Ionic. And if it is shared between atoms, it is called covalent, right? And if it's shared, we know we can share them equally or unequally, and we have terms for those. So what's important to know is these attractions between molecules are just that they're attractions, but there's not actually any bonding taking place. Okay, so no exchange of electrons, no bonding whatsoever. So they do not involve that. So from that point of view, then, these attractions are not true bonds. Okay, so no bonds taking place, just attractions. All right, so in order to describe, there are 4 types of intermolecular attractions that we're going to look at. So 4 types. And I'm going to put them in order of strength. Okay, so we got 4 types in order of strength. The first one is called an ion-ion force. What do you think is involved in the ion-ion force?
2 ions.
2 ions. So the attraction, with an ionic bond in that sense, it's not, we say there's a bond there, but once you have the actual ions present, the positive and negative ions aren't exchanging electrons at that point. They are just attracted to one another because they're opposite charges. So this is the strongest attraction because we have distinct positive and negative charges attracted to each other. Okay, so much like where we have positive, a negative, a positive, a negative. Something like this, we have those ions there. Okay, so that's the first type. It is the strongest. Here we're going to introduce the second type. And the second type is called a dipole-dipole attraction. And you notice I'm putting some space between 1 and 2. That's on purpose. So if you're doing that, make sure you leave some space there between 1 and 2. What we're going to see is that our third type is actually up here in terms of strength, but I introduce it after. So our second type here is dipole-dipole. This one involves polar molecules. Remember, if something is polar, what does that mean? So ion-ion is the ionic one. The rest of these are involving covalent compounds. So if we have a polar molecule, what are we saying in terms of the way the electrons are shared in the bond? Almost, but what does this mean qualitatively? Are the electrons shared equally or unequally?
Equally.
It's polar, it's unequal. It's polarized, which means one side has more of the electron density than the other. So if we have something, so this would be unequal, but you were right, you said the electronegativity difference was 0.4 to 1.7. But the important aspect here is that it's an unequal sharing of the electrons within the bond. So if we have a bond here, let's say carbon to fluorine, which end is polar and which one, right guys, the way I should say that is which end is more electronegative? Fluorine. So we would see something like this. or we can draw the dipole like this with the arrow, with the plus sign by carbon. Carbon has more positive character, fluorine's more negative character. So what it's indicating here for dipole-dipole is the following, that a positive end of one molecule is attracted to the negative end of a nearby molecule. So if you have something there where you have a positive and a negative end, then it finds a similar molecule with that positive and negative end. And we're going to see attractions like that, such as if we have C and F, something like this, where this is more that negative, this is more that positive. And when it comes in contact with another molecule that has that bond, it'll be the positive end that goes near that negative end. So notice the attraction here between the negative and the positive. Okay, opposites attract, so that is an attraction. It's not a real bond. We're not exchanging electrons, but we're matching up these partial positive and partial negative ends between molecules. So if we go back to the very beginning of the definition, we said these attractions are just that. They're attractions between two or more molecules. Okay? And for an attraction, typically it's going to be a positive and a negative. When we looked at ion-ion, we have a distinct positive and negative charge. And so the molecules arrange themselves so that it's positive, negative, positive, negative. We have those opposite charges attracting each other. Okay? When we get to things that involve covalent compounds, which is going to be the rest of this, the way covalent compounds are set up is they share electrons between bonds. And again, we want attractions between molecules. So in a dipole-dipole attraction, if we have a polar bond where one end is slightly positive and one is slightly negative, then it's going to team up with another molecule nearby such that the positive end is going to be near the negative. So the way this is arranged, if we have multiple molecules arranged, we have negative and positive that are attracted to each other. The difference being that with covalent, these are partial charges. They're not full-on independent individual charges like ionic bonds have. But it's just because we do have this positive and this negative attractions, or I shouldn't say attraction yet, it's a dipole, right? There's an imbalance in electron density, so one end is more electronegative than the other. And because of that, to help stabilize itself, when there's another molecule nearby that has a similar polarity, right, where it's got the imbalance of electron density, they will team up in a way that we have this negative and positive attraction to make it more stable. Does that clarify it? Okay. Anybody else so far? Okay. So that is the dipole-dipole attraction. I said it involves polar molecules, and because I said molecules here, remember it is covalent. Okay. The next type of intermolecular attraction, so our third one, I'm actually putting back up here above dipole-dipole. This third one is called hydrogen bonding. How many of you have heard of hydrogen bonding? A few of you. What do you know about hydrogen bonding? Okay.
Won't they bond with themselves?
If it's hydrogen bonding? Not quite. Braden? So keep in mind, we said Intermolecular attractions, there's no exchange of electrons, which means there are no bonds taking place, even though we have bonding in the name of this one. Crazy, okay? But that's what it's called. So hydrogen bonding, what we say is that we have, and I'll put it in blue to differentiate the colors here, is a hydrogen bonded on a, or bonded to a highly electronegative atom, such as fluorine, oxygen, or nitrogen. So if we have, for example, water, oxygen is a highly electronegative atom. It has an electronegativity of 3.5, arbitrary value, but it's still a high value. And so we're saying that hydrogen is bonded to a highly electronegative atom like oxygen, and that hydrogen is attracted to a highly electronegative atom like fluorine, oxygen, or nitrogen on a nearby molecule. Okay. So I'll let you write that down real quick. Okay, so again, hydrogen is bonded to a highly electronegative atom, like fluorine, oxygen, or nitrogen, like in water, and that hydrogen is attracted to a highly electronegative atom on a nearby molecule. So if we set up another water like this, then we're saying that a hydrogen is attracted to a highly electronegative atom nearby. And we could set up a whole network like this of water molecules, and that's what gives water some of its unique properties, like having a high surface tension, the way it behaves as a liquid and then eventually becomes a gas. The fact that as a liquid it has such a high boiling point. Okay, and where I mentioned the FON here, here's a way to remember the atoms that are used in hydrogen bonding, is we say hydrogen bonding is fun. What's funny is my first year of teaching in Indiana, I had a student with the last name Fun, F-O-N. And so I joke, hey, you're hydrogen bonding today. And I still remember it to this day. And that was, oh goodness, that was 5-6 years ago. So that means, I think he's probably at this point done with college and in his career. Time flies. I don't know, if I did something right, he's off doing something making more money than I am, right? Good career. So hydrogen bonding is fun. Just keep that in mind. So if you're asked a question like, how come, HCl, I'll put it here, how come, like if we compare HCl versus water, how come water has like a higher boiling point, or how come water behaves a certain way compared to HCl? And we would say, because what?
Electronegativity.
What about it?
And the hydrogen bonds, it's bond.
Okay.
It has an O, so like it's like higher.
Okay, so O is higher than chlorine.
So it's like more bond together.
Okay.
More together.
So HCl, based on what we've said so far, what's the electronegativity of H? No.
Like 0.01.
Try 2.1. What's chlorine?
3.5. Right? No.
I think it's 2.9. So the difference, 0.8, means that HCl is still a polar molecule, or I should say has a polar bond. Water is also polar, so they're both polar molecules. The difference, though, is that hydrogen or water here has hydrogen bonding because it has that highly electronegative atom such as oxygen. So it's going to behave differently than HCl would. Caitlin?
Oh wait, no, got it, never mind. I gotta just say things out loud.
That's fine, I do it too. Now, the point of doing the electronegativities was just so we could clarify and state that HCl is in fact a polar molecule. Okay, and water is also polar, so they're both polar, but the difference lies in the fact that HCl only has the dipole-dipole attraction so far, whereas water has the dipole-dipole and it has hydrogen bonding. Okay, so water, because it has more of these intermolecular attraction types than HCl, means that water is going to be kind of a stronger molecule. It's going to take more to break it up or change it in some way. All right, the very last one here that we'll cover so the fourth one is called London Dispersion Force. Or LDF. It's also called van der Waals forces for short, or not for short, but differently. So van der Waals. So the idea going on here with LDFs, or London Dispersion Forces, these are the weakest of the attractions. They're present in all covalent compounds. Okay. So even though all covalent have them, they're still the weakest attraction. So here's what's going on. Let's say we have, I don't know, the model I always remember is taking a helium atom. And a helium atom has 2 electrons. Do you agree with that statement?
Sure.
Okay, good. So the idea is that every once in a while, you know, we know from Heisenberg that helium does in fact have 2 valence electrons, or I should say 2 total electrons, and we know they're somewhere around the nucleus. Do we know where they are at any point in time?
No.
No, we don't know their exact location. We don't know how fast they're moving. We know due to probability in the electron cloud model that they are there. Or at least I shouldn't say we know, but we assume that they're there. And so based on that assumption, what we're also assuming is that on average, they are on opposite sides of the molecule or the atom from each other, because you don't want 2 like charges right next to each other, right? That would create a dipole of sorts, a charge differential. And so if we have them separated, one here and one here, then we're usually pretty stable. But every once in a while, we get an imbalance of electrons, and we end up with both electrons on the same side of the atom. Okay, and so what happens in that case then is we end up with a slight dipole. Okay, so just saying, hey, you know, we can get this temporary dipole because we have this sudden imbalance of electrons around the nucleus. Does that part make sense? Like we're assuming they're on opposite ends, but once in a while they may end up on the same side. That's not as stable. It creates an imbalance. Okay. So in words, we would say the following, that we get a temporary polarity due to an imbalance of electron around the nucleus. Okay, so we get this temporary polarity due to an imbalance of electrons around the nucleus. And this in turn can induce or create all of a sudden a dipole on a nearby atom. Okay, so what that would look like is if I put another atom up here that may have had one electron on the left side and one on the right. Now that we have this dipole going on here, that's going to push the electron on a nearby molecular atom to the other side. So we end up with electrons both on the same side over here, where now we have this dipole taking place. And so notice the negative and positive between them. So we do create this sort of dipole attraction, but it is just temporary, which means it's very weak.
Why do you have like by the atom looking thing? Why do you have those?
What do I have? What?
The 8. What is that?
These are the lowercase delta.
Oh.
So it's partial positive and partial negative to show that there's a polarity going on there. So before we had like one electron on one side, one on the other. And if for some reason temporarily they end up on the same side, then we're slightly negative on one side, which means we're a little more deficient on the other.
Okay.
So that's that temporary polarity due to this imbalance of electrons. And when we get that polarity, it then initiates or creates a polarity in another nearby atom.
Okay.
And so they kind of line up that way. And so then we get this negative and positive type of relationship. Bearing in mind, though, again, it is temporary. So it is the weakest of our attractions so far. All covalent molecules have them, but it is the weakest.
Would that also work with protons and nucleus?
You know, the nucleus is so small and so dense that I'm not sure they could look to see if there's at any point in time where you have more on one side of the nucleus than the other. I'll let you figure that one out. Okay. Can you put into words what specifically? Okay. Okay. Let me finish up my last thought that goes with dispersion forces, and then I'll try to sum it all back up together and see if that helps, and if not, we can chat after. Okay, so the last thing that I want to say about dispersion forces here is the following, that dispersion forces increase in strength as the size of the atom increases, or the length of an atom chain, which would be related to organic chemistry, where we have a long chain of carbons bonded together, if that chain increases. So basically, as the size of the atom or the molecule increases in size, then we're going to have a greater effect from the dispersion force. And think about it, if you have a big atom, let's say, we just compared helium. Helium has 2 electrons. But if we compare something like, I don't know, argon, notice with argon, which you can't even see there. Oh, there we go. So 1, 2, 3, 4, 5, 6, 7, 8. Argon, you might end up with notice all these outer electrons here, they're all on one side. So the fact that the atom gets bigger, you can have more of an effect or pronunciation of that dipole than in a smaller atom. So we're just saying as the size of the atom gets bigger, the strength of that specific attraction gets bigger.
Oh, with argon, does this change the electronegativity?
Nope. Because electronegativity is its desire to control an electron pair. In fact, these examples here, helium and argon, activity because they already have their octet filled. So they're already stable. Okay, so stay with me, folks, here. So we have these 4 types. All right, so I'll kind of sum up to get to where we were. So we started with ion-ion, and ion-ion is only ionic. Okay, and here we have distinct positive and negative attractions. It's just how the molecules are set up. Right, so we have like the positive, negative, and those are actual attractions. And then we went down to dipole-dipole, which is for covalent molecules where the electrons are being shared between atoms. So it involves polar molecules, which we said was an unequal sharing of electrons based on, you could do it based on electronegativity, but just the idea that you have an atom or 2 atoms, one is more electronegative than the other, like fluorine is much more electronegative than carbon. So we show the direction of the dipole, indicating that we're going from positive toward the more negative atom. And because this bond has a dipole set up, well, if we put it in the context or vicinity of other bonds or other molecules, we're going to want to have the attraction set that, or such that the negative and positive attractions go together. Keep in mind, there isn't an actual bond here. It's just an attraction between negative and positive. Okay, are we clear on the idea of the attraction? It's not a real bond, it's just an attraction between negative and positive or opposite charges. With ionic, we had actual distinct charges, like legit charges. Covalent, they're partial charges because they're still bonded, they're physically bonded, but one side has, like I drew kind of the lopsided shape here, fluorine being more electronegative has more of that electron cloud around it than carbon does. And if we set that up in a progression, then the negative is going to be attracted to the positive on a nearby molecule. And same thing as we keep going. Okay. And then we talked about hydrogen bonding. And I guess you can even see all that there that I was pointing to. With hydrogen bonding, we still are going to have an attraction between hydrogen, in this case, which is more partially positive, because oxygen is more negative, hydrogen is positive. So notice the hydrogen, which is partially positive from that dipole, is then going to be attracted to a negative atom or partially negative nearby. It's not a true bond, hence there's no solid line, but the dashed line says there's an attraction between something partially positive and something partially negative. And we're more specific because while this is a dipole-dipole, by definition, we're being more specific in saying that hydrogen that's bonded to a highly electronegative atom, like F over N, isn't attracted to an F over N on a nearby molecule. Okay? So we're just, the way we're defining it, it's still dipole-dipole, but it's more specific. In fact, it's a much stronger variant of the dipole-dipole attraction. And then we went down to London dispersion forces, and we said these are the weakest attractions of all. They occur in all covalent, whether polar and nonpolar. And so we drew the picture to demonstrate, you know, if we start initially where the electrons are on opposite sides that we're assuming, that once in a while they are maybe an imbalance, that they may end up on the same side of the atom, which would be this temporary polarity. So we have a side that's electron poor or electron deficient, and then the other side is more electron rich. So this side is electron poor, and this side is electron rich because it has electrons more on that side. And if we create this temporary dipole, right, that's what we're doing. It's temporary. It's another books would call it instantaneous. And then what happens is it induces or establishes the polarity to happen in another atom. The idea being that we can get a negative and a positive to be attracted. Okay. And then we said, as a way of looking at it in the broad scope of things, as your atom gets bigger or your molecule gets bigger, you're going to have an increase in the strength of that force because you have a greater likelihood of dipole being stronger. Okay, more electrons over on one side. So where does this come into play with some of our other things? I know I said I mentioned boiling point, but I'm going to start with surface tension because that's our lab for tomorrow. Okay, so for your lab tomorrow, your objective is going to be to observe the surface tensions of several different liquids. And by the end, what you want to do is write a conclusion concerning surface tension and the strength of intermolecular forces of the liquids in the experiment. The liquids that we're going to be dealing with include water, soapy water, okay, which you have, so like you have water, but soapy, it's like soap has these things, I've heard them called as micelles, and they kind of get in the way of the water molecules. So if you think of water and all the hydrogen bonding going on, soap particles kind of get in the way of that attraction. So soapy water isn't as strong of an attraction as water, let's say. And then you're going to have ethanol. I write it as ETOH. And ethanol, sorry, ignore that scribble, is C2H5OH. So notice we have a hydrogen bonded to an oxygen. So what kind of attractions are present for ethanol?
Van der Waals
Mm-hmm.
and hydrogen bonding
Mm-hmm.
and dipole-dipole.
Yep. So if it has hydrogen bonding, it automatically has dipole-dipole because it's a special type of dipole-dipole. The flip side is not true. If you have dipole-dipole, you don't necessarily have hydrogen bonding. Right? What's the saying that a square is a rectangle? But a rectangle is a, no, a square is a rectangle is not a square, right? Or a square is a rhombus, but a rhombus isn't a square, based on their geometry definitions. Anyway, and then your other one is isopropanol, or rubbing alcohol. And the structure for that is the following. And so we would expect, like compared to water, that ethanol and isopropanol get stronger dispersion forces perhaps because they're bigger. But keep in mind about how much hydrogen bonding you can have and how these start to get buried down by other parts of the structure. Okay, so we'll look at this a bit more tomorrow. In the meantime, have a good weekend or a good afternoon.